Okay, we have the Laplace equation del 2u del x square plus del 2u del y square equal to 0. So the question is change it into the polar form. So we want to change this variable x comma y, those are independent variables, to the new variables r comma theta. Well, how can we do it? Well, we know that. Okay, let's recall. Let's draw something like this. We have x-axis and y-axis here. Those x and y are independent variables, and then we have initial ray, and we have an angle, let's say theta. Generally we take in any anti-clockwise direction, and a point is given by r comma theta, where r is distance from origin to that point. Now we know r and theta are independent, just like x and y are independent. And also we know that, well, x equal to r cos theta and y equal to r sin theta, and that will obviously, if you square it, you'll have x square plus y square equal to r square. Notice that I'm writing r in theta in red, x and y in blue. You'll see it y. Okay, now in order to convert it into polar form, the Laplace equation into polar form, the equation del 2u del x square plus del 2u del y square equal to 0 is also referred as Laplace equation, and we would like to convert it into polar form. Let's recall something called chain rule. You see, u depends on x and y. Let's differentiate u partially with respect to x, that is our del u del x. So we want to apply chain rule, so let's write first of all, we have by chain rule, we have by chain rule, what do we have? Del u del x equal to del u del r, u depends on r, then del r del x. Is that enough? Answer is no, because r depends on x as well as u depends on r as well as theta. If you are differentiating partially with respect to r, then by chain rule you have to add something more, that is your del u del theta, then del r del x. Now similarly we'll have something like del u del y, that is partial differentiation of u with respect to y, and if we can then again double differentiate it. If you can write this completely in terms of u r and theta, here also you can write it completely in terms of u r and theta, then we are done. So Okay, now you can just write it as UR, that denotes partial derivative of u with respect to r, and then I can write Rx. Notice that your x is being written in blue. So we have old coordinate system x comma y, xy coordinate system, and we have new coordinate system that's in red, r comma theta, just for easier grasping. Everything we want it in terms of red now. Okay, now ur, that's partial differentiation of u with respect to r. Then you have u theta, that is partial differentiation of u with respect to theta. Then you have partial differentiation of r with respect to x. Okay? Sorry, I made a mistake. If you, it's something like cancelling della and you are left out with same thing. Something like cancelling, you should have cancelled del theta here, and then you are left with the same thing. You can remember that way. So you have u theta and theta x. You see, if you can remove this term, then at least you have del u del x in term of polar coordinate system. Let's do it. Can we remove? If we can remove this Rx, that is partial derivative of r with respect to x, and if you can replace theta x, then you have at least del u del x in term of polar coordinate system. Okay, how can we do it? Okay, now let's again utilize some formulas. So we want partial derivative of r in term of x partial derivative of r with respect to x and partial derivative of theta with respect to x to be expressed purely in term of polar coordinate system. How can we do it? Let's see it. However, we have x square plus y square equal to r square, and we have tan theta equal to y by x. We have x square plus y square equal to r square and tan theta equal to y by x. This you can easily do it by taking y equal to r sine theta, x equal to r cos theta. Here also you have already done it. X equal to r cos theta, y equal to r sine theta. So you take cos square plus sine square equal to 1. You will have r square here. Here you have sine theta by cos theta is tan theta. So this can also be written as theta equal to tan inverse y by x. Now let's see, can I get Rx and theta x and something? Okay, can we get Rx and theta x? Okay, differentiating above equation partially with respect to x, what do we get? Okay, let's do with respect to x as well as with respect to y, because later on we need del u del y as well. Differentiating above equation partially with respect to x and y. Now, differentiating above equation partially with respect to x and y, what do we get? Well, del x of x square is just 2x. Del x of y square is 0. Del x of r square is 2r del r del x. In other words, we know that x is r cos theta, so let me cancel 2 here. Okay, before that, let's do partial differentiation with respect to y as well. If you do with respect to y, then you have 2y equal to 2r del y. Okay, let's write r in red color. That's what everything we want it to be in red. So, okay. Now x equal to r cos theta. So let me just write it as r cos theta. That's, I think I can write it in red because r and theta are, and I can write rx. Y equal to r sin theta. So let me write r sin theta. I can cancel 2 out, equal to r into ry. So if you cancel r, so what we did is, instead of x we wrote r cos theta, instead of y we wrote r sin theta. Then del r del x can just be written as rx, del r del y can just be written as ry. Now you can see that if you cancel r, that we can always do it, then we have rx is nothing but just cos theta. So if we substitute here, we can, instead of plugging rx here, we can just write cos theta here. Then you'll see that, well, you'll have everything in terms of r and theta. Rx we can write it just as cos theta, and ry, what about ry? What about ry? Well, ry is just sin theta. Ry is just sin theta. Instead of ry, we can just write sin theta. So we have so many equations. Let's say this is our equation 1. This is our equation 2, and we just did, and this is our equation 3. We have equation 1, the every del u del x is almost expressed in terms of r and theta and u. The only problem is you have x here and you have x here. that you can see that, well, you can remove it from here. Therefore, from equation us, that doesn't give. Theta x is not known till this point. So differentiating above equation partially with respect to x and y. So we did this x squared plus y squared equal to r squared. We did differentiate it partially with respect to x and y, and you have the result. What about this one? Theta equal to tan inverse y by x. Let's differentiate it partially with respect to x and y. What will I get? Okay, so let's differentiate. Okay, let's recall once again. We have theta equal to tan inverse y by x, and we want to differentiate it partially with respect to x and y. If we do it with respect to x, we have theta x equal to del x of tan inverse y by x. That's equal to 1 by 1 plus y squared by x squared. Then del x of y by x, that is y into minus 1 into x to the power minus 2. So you can simplify it. You'll have y by x squared plus y squared. Now you know y equal to r sine theta, and x squared plus y squared is r squared, so that is just minus sine theta by r. Aha. Let's do it partially with respect to y as well, that we need it subsequently. Theta y equal to del y of tan inverse y by x. Once again, tan inverse, if you differentiate it, you will get 1 by 1 plus y squared by x squared. Then del y of y by x, that is just 1 by x. And if you simplify it, you'll have x by x squared plus y squared. Now, once again, x equal to r cos theta, x squared plus y squared is r squared, so cos theta by r. Okay. Now, what do we have? Well, earlier we were having del u del x is equal to ur into rx. That's u depending on r only, u dependent on, partial differentiation of u with respect to r only, and partial derivative of u with respect to theta only. But we have the problem with the partial derivative of r with respect to x and partial derivative of theta with respect to x. We want to get it in terms of r and theta only, but rx we have cos theta, ry we have sine theta. That's that much we have. And then now we have theta x equal to minus sine theta by r. So let's write it as equation 5, and then this one is equation 6. Therefore, by equation by equation can you see here 1 here? By equation 1, your rx you can write it in terms of cos theta by equation 1, then 2, then you have problem with theta x, and theta x you can write it in terms of minus sine theta by r 5, 1, 2, and therefore by equation 1, 2, and 5 we have, okay, let's write equation 1 once again. We have del u by del x equal to, equation 1 we have u r, that we will not change anything, rx partial derivative r with respect to x, that turns out to be just cos theta plus u theta, that will not substitute anything, then theta x by equation 5 is just minus sine theta by r. So what do we have then? u r, rx is cos theta plus u theta, and theta x is minus sine theta by r. Bingo. Minus sine theta by r. Bingo. We got it everything in terms of r and theta. But that's only del u del x. What about del u del y? Okay, we can do it similarly. First by chain rule, del u del y equal to, we have chain rule, del u del y equal to okay, let's just do it. Del u del y equal to del u del r, then you have ry, that we need to plug in something, plus del u del theta, then we have theta y. Ry, did we already compute it? Yes. Ry is just sine theta. So del u del r, ry is just sine theta. Del u del theta and theta y is just theta y is just cos theta by r. Cos theta by r. Theta y is just cos theta by r. So let's write it in the compact form. U r sin theta plus u theta cos theta by r. Now is that enough? You got del u del x, del u del y, but you want double derivative of u with respect to x and double derivative of u with respect to y, totally in terms of r and theta. What to do then? Well, pretty simple. Not that simple though. Del 2u del x square, that is double derivative, I should say double partial derivative of u with respect to x is nothing but del x of del u by del x. I just wrote it to be small and I wrote it to be big because once again this is a function that depends on x and y, as well as if I say in the new coordinate this is a function that depends on r and theta. So we can apply chain rule. So what do we have? Del theta of ux, that is your del u del x, then del theta del x, then theta x. We have already computed theta x in terms of r and theta. Did we do it somewhere? Theta x in terms of r and theta. Where is it? Yes, we have it. Lucky. Del theta of ux that we need to compute. We have already computed theta x in terms of r and theta. Del theta of ux that we need to compute. Ux is also already computed in terms of r and theta. But chain rule is not complete. We have del r of ux then we have del r del x. That also we have already computed in terms of r and theta. So what is del theta of ux? Well, okay, so let's write expression for ux. Let's take it out from what we have obtained in equation number how many equations do we have so far? 6 we have, so let's say this to be 7th equation. So therefore by equation 7 theta x and rx, what about those? What were the equation? Theta x and rx. Rx is equation 2 and theta x is your equation 5. 7, 5, comma 2. By 7 you have ux in terms of r and theta. So that is your ur cos theta minus u theta sin theta upon r, that's just ux. See, everything we have got in terms of r and theta now, lucky guy. But that's not enough. But theta x, what about theta x? Theta x is by equation 5, theta x is just minus sine theta by r. Theta x is just minus sine theta by r, but that's not enough. You also need del r of ux. So let's write it out. Del r of ux. Your ux is ur cos theta minus u theta sine theta by r. Then, okay, you should distinguish that this is just multiplication. Then you have Rx. Where is Rx? That is by equation number 2. Rx is just, by equation 2, Rx is just cos theta. Okay, let's simplify this. Okay, so del theta, you have got sum of two functions. You can easily differentiate it, and then you have product of two functions as well. So let's do it directly. U r theta first function into derivative first function into second function, plus ur into derivative of cos theta with respect to theta is minus sin theta. So we have just differentiated this portion. We have just differentiated this portion. What about the other one? Let's do it other portion as well. Minus we need to multiply it by minus sine theta by r as well. What about this portion? Del theta of u theta, that is u double theta, that is double partial derivative of u with respect to theta. Then sine theta by r as it is, derivative first function into second function, then first function into derivative second function. Partial derivative sine theta is cos theta. At last we need to multiply everything by minus sine theta by r, because that's what was there previously. Then we have del r of same thing. Okay, we have to apply product rule. U r cos theta plus, you can take cos theta to be constant, so lucky guy, because you are differentiating partially with respect to r, so cos theta is constant, so that's done, so no need to use product rule. And here u theta sine theta, that you can take it as constant, and r to the power minus 1. If you differentiate r to the power minus 1, minus 1, r to the power minus 2, minus will make it plus. I have already done it. R to the power minus 2, so just r square. Everything to be multiplied by cos theta. Okay, do we have some term cancelling? URR no. U theta plus u theta sine theta cos theta by r square, that's also no. Okay, we don't have anything to cancel, but we have something to simplify. cos into cos, cos square theta u r. That's it. What about u r theta? U r theta, we have only one term, minus sine theta into cos theta by r u r theta. Whatever u theta r, we don't have u theta r anywhere. Then you have u r. U r is your sine square theta by r times u r. U r gone, u r theta gone. Then u theta. U theta, you have two terms, sine theta cos theta by r square, and here also sine theta cos theta by r square. So you can add it, 2 sine theta cos theta by r square, and then u theta. That's partial derivative u with respect to theta. At last you have u double theta. U double theta, what's the sign? Sign is positive, plus sine square theta by r square u double theta. So you got everything in terms of r and theta. You have started with double derivative of u with respect to x, and you got it with so many terms, but all of them are there, either r or theta. What about del to u del y square? Okay, same thing we have to repeat again. Del to, not same thing but similar thing we have to repeat again. Del to u del y square is del y of del u del y. Okay, so del to u del y square, that is partial double differentiation of u with respect to y, is partial differentiation of first partial differentiation of u with respect to y. That we got this quantity we have already done it before. Del u del y is first partial differentiation of u with respect to y. Let's shall I write equation number? Yeah, I think I should write equation number 8 here. By equation 8, by equation 8, and here I think I can write similarly, so maybe I can similarly by equation 8. By equation 8 you have, where is equation 8? That's the one. Want double partial differentiation of y, double partial differentiation of u with respect to y, and that's by equation 7. You have u r sine theta plus u theta into cos theta by r. U r sine theta, u theta into cos theta by r. That's by equation 7. Now what to do then? Chain rule. Del r of u r sine theta plus u theta into cos theta by r, del r of u r sine theta, then you have ry plus del theta Then you have theta y. Okay, ry once again sine theta by equation 3. Ry is sine theta by equation 3. And what about theta y? Theta y is your cos theta by r. Let's plug in there and let's apply product rule. Maybe somewhere here also we don't need product rule. Here we don't need product rule, and here also you don't need product rule. Okay. So you can, if you are differentiating partially with respect to r, then you can treat theta to be constant. So sine theta u r plus. Oh, you don't have to apply product rule here. Lucky guy. U theta cos theta into minus 1 r to the power minus 2 once again sin theta is independent of r, so sin theta you just take it as constant, double derivative of u with respect to r. I should also say partially. Then cos theta, sin theta, again you can treat it as constant. If you're differentiating r to the power minus 1, you have minus 1 r to the power minus 2. Then ry is just sin theta. Here, u depends on r and theta. Sin theta will depend on sin theta only. U depend on r and theta. R is independent of theta. Plus u depend on theta, so u r theta, that is first partial differential with respect to r, then with respect to theta. Del theta of sin theta is cos theta plus u r as it is. U r as it is. Del theta of sin theta is cos theta plus u r, if you are differentiating with respect to theta, sin theta as it is. Let's check it. First function you leave it as it is, differentiate second function, plus you differentiate first function, then leave second function as it is. Okay. Plus you can treat 1 by r as constant if you are differentiating with respect to theta. U theta, if you differentiate it, you get first function differentiated cos theta as it is. Then first function as it is, derivative cos theta is minus sin theta. You need lots of bracket here. So it is curly bracket. Not exactly so curly though. Check it. U r, first function as it is, sine is cos. Differentiate first function, sine as it is. Then 1 by r is constant. U theta, if you differentiate it, you get double differentiation of u with respect to theta. Cos theta as it is. Plus first function as it is, derivative cos is minus sine. Yeah. Now theta y. What is theta y? Theta y, let's recall somewhere cos theta by r. Cos theta by r. So should multiply it by cos theta by r. Can we do it here? Yeah. Quite a small space. just sufficient for writing cos theta by r. Okay, so we got this much. Now let's simplify it then. URR sine square theta then UR theta, what are the terms there? UR theta sine theta cos theta by r, UR theta, that's only one term. I think I forgot something, so sad. Sine theta URR, U theta sine theta URR, U. Oh, I forgot something here. While applying product rule, sine theta double derivative U plus UR derivative sine theta is, no, it's okay. It's okay. It's okay. Yeah, it's okay. Perfectly okay. So we have sine square theta U double derivative with respect to r. Then you have UR theta just plus UR theta into sine theta into cos theta upon r. Then u double derivative r, UR theta, then let's say UR plus UR into cos square theta by r. Then you have, do we have something cancelling? No. U theta you have got, yeah, U theta you have got something common. U theta you have got plus U theta, I think I should have minus here, minus sine theta into cos theta by r square into u theta, and you have sine theta into cos theta by r square into u theta, so that is occurring twice. At last you have plus cos square theta u theta theta by r square. Okay, so how many equations do we have? We have equation 8. Let's take this equation. Somewhere here is equation 9. And at last, this one is equation 10. Equation 9 gives us partial derivative of u with respect to x totally in term of r and theta. Equation 10 gives us partial derivative u with respect to y totally in term of r and theta. Once again, equation 9 gives us partial derivative u with respect to x totally in term of r and theta. That's your equation 9. And equation 10 gives us partial derivative of u with respect to y totally in term of r and theta. So adding equation 9 and 10. We have, okay, URR cos square theta, URR sin square theta. If you add it, you'll just get, okay, first of all, left hand side, what you have? Left hand side, you have del 2u del x square plus del 2u del y square equal to, on the right hand side, you have cos square theta URR plus sin square theta URR. That's just URR, since sin square plus cos square equal to 1. Then UR theta, you see that minus sin theta cos theta UR theta, and here what do we see? UR theta plus sin theta, so that can be cancelled. UR theta gets cancelled. All right. UR gets just sin square plus cos square equal to 1. So you have got UR by R. Then you have U theta 2 sin theta cos theta by R square in your double differentiation of u with respect to x, and in the double differentiation of u with respect to y, we have u theta or minus 2 sin theta cos theta by R square, so that will also get cancelled. And at last, sin square theta by R square u double theta, that's one term here, and here in the other one you have cos square theta u double theta by R square. So sin square plus cos square is 1. So u by R square. Now we know that Laplacian is 0. That's 0. Let's simplify it a little bit. And you have R square UR plus RUR plus U theta theta equal to 0. Bingo, we got everything in terms of R and theta. And that's your Laplacian in polar form, Laplace equation in polar form.